Okay, so you missed a few robotics lectures, and that exam is coming up fast. Don't worry, you've come to the right place. In the next few minutes, we're going to build a robot from the ground up. Not with metal and wires, but with all the core concepts you absolutely have to know. Let's get you ready to ace this test. You almost have to start here, with Isaac Asimov's famous first law from way back in 1942. This is the idea that really set the stage for how we imagine robots in science fiction. But here's the thing, that's the sci-fi version. We're about to get into the real deal, building a real-world robot, piece by piece, starting with what a robot actually is. All right, so if the exam asks, what is a robot? This is the gold standard answer you're going to want to use. It comes from the Robotics Industries Association. And the keywords you have to remember are programmable, multifunctional, and manipulator. See, it's not just any old machine. It's one you can teach to do a bunch of different physical jobs. So, before we jump in and start putting the pieces of our robot together, let's ask a fundamental question. Why? Why do we even need them in the first place? Where did this whole idea come from, and what problems are they supposed to solve? This is part one of our build. It's pretty wild how fast we went from a play to the factory floor. The word robot itself actually comes from a Czech word that means tedious labor, which is perfect, right? Less than 40 years after that play, this guy, George Devol, patents the first real robot. And then, boom, by 1962, the Unimate is already on a General Motors assembly line. Every step here, from the Puma to Asimo, was a huge leap forward. So what's the big idea? Why go to all the trouble of building robots? Well, it really boils down to these four things. They're way faster than us, they're more precise, and they never, ever get tired of doing the exact same boring thing over and over. But maybe the most important reason is safety. Robots can go places we can't, or at least where we shouldn't, like dealing with dangerous chemicals or working in crazy high temperatures. Okay, so we've covered the why. Now for the fun part, the what. Let's actually start assembling our robot, piece by piece. What are the absolutely essential components that make a robot, well, a robot? And here's the best way to remember all this for the exam. Just think about the human body. It's a perfect analogy. The manipulator is the arm, giving it structure and reach. At the end is the end effector, which is like the hand, holding a tool. The movement comes from the actuators. Those are the muscles. Robots can feel their environment using sensors, which are their senses. The whole show is run by the controller, which is the brain. And of course, none of it works without a power supply, which is the heart. First step, the manipulator. Super simple. This is the robot's arm. It's just a series of links connected by joints, and its one and only job is to get the hand, that end effector, positioned exactly where it needs to be in three-dimensional space. And what's at the end of that arm? That's the end effector. This is the business end of the robot, the part that actually does something. It could be a simple gripper that picks things up, or something way more specialized, like a welding torch, a paint sprayer, you name it. And of course, none of this works without the controller. This is, without a doubt, the brain of the whole operation. It's the computer that's running the software, processing all the information from the sensors, and telling the actuators, the muscles, exactly how to move to get the job done. All right, our robot is built, at least in concept. It's got an arm, a hand, a brain, but how well does it actually work? Now listen up, because this next part is almost guaranteed to be on your exam. It's all about how we measure a robot's performance. And that leads us straight into a classic exam question. You will almost certainly have to define and explain the difference between accuracy and repeatability. They sound kind of similar, but trust me, they measure two totally different things. Okay, the easiest way to nail this concept is to think about throwing darts. Accuracy is how close you get to the bullseye you are aiming for. Simple. Repeatability, on the other hand, is about how tightly clustered your shots are. You can throw 3 darts and have them all land touching each other, but way over in the corner, far from the bullseye. That's great repeatability, but terrible accuracy. For a job like welding, sometimes all you need is to hit that same spot over and over, so repeatability can be even more important. All right, next up is a term you'll hear all the time, degrees of freedom, or DOF for short. This sounds complex, but it's really not. It's just the number of unique ways a robot can move. And here's the key. Every joint on the robot, whether it's one that slides or one that rotates, adds 1 degree of freedom. So, what's the magic number in robotics? It's 6. Why 6? Well, a robot with 6 degrees of freedom can reach any point in 3D space with any orientation. Think about it.
3 for position, moving along the X, Y, and Z axes, and 3 for orientation. That's the wrist being able to roll, pitch, and yaw. With 6 DOF, that robot has complete freedom.
Okay, so we know how to measure how well a robot performs. Now let's talk about the different types of robots you'll see out there. They're usually grouped by their physical structure, how they're built, and by the kind of control system that's running the show. Now, for the exam, there are 4 main designs you've got to know. Cartesian robots are the ones that move in straight lines, like a 3D printer. Cylindrical and spherical types mix in some rotation with that linear motion, and then you have articulated robots. These are the most common ones in big factories. They use all rotating joints, pretty much just like your arm. Okay, another huge concept. How does the controller actually, control things? This comes down to 2 systems. An open-loop system is basically fire and forget. The controller sends a command and just assumes the robot did it right. But a closed-loop system is much smarter. It uses sensors to get feedback on where the arm actually is, compares that to where it should be, and makes constant little corrections. It's essential for anything that needs to be super precise. And one last thing on control. How does the robot move from point A to point B? There are 2 main ways. A point-to-point system only cares about the destination. It needs to get to specific spots, but it doesn't really care how it gets there. Think spot welding. A continuous path system, though, is all about the journey. It needs to follow a precise, smooth path the entire way, which is critical for something like spray painting a car.
Whew. Okay. We've built our robot, we've defined how it moves, we've even classified it. To bring it all home, let's look at where you actually see these things in the real world, and then we'll do a lightning round review to lock it all in for your exam.
You know, when most people think robot, they picture those giant arms in a car factory, right? And yeah, that's a big one, but they are everywhere now. From the incredibly precise robots used in surgery, to the rovers exploring Mars, to that little vacuum cleaner bumping into your furniture. They're all built on the same core ideas we just talked about. All right, deep breath. This is it, your final cram session recap. If you only have space in your brain for 5 things, make it these 5. 1. A robot is programmable. 2. Accuracy and repeatability are not the same thing. 3. DOS is all about flexibility. 4. No Cartesian versus articulated robots. And 5. Closed-loop control uses feedback to be accurate. Got it? Awesome. And look, to make this even easier for you, here are the top 5 questions that show up on exams all the time. If you can sit down and write a solid, clear answer for each of these, you are going to be in fantastic shape for your exam. Good luck. You've got this.